Hi everyone, my name is Jeremy Morgan. Today I'll be presenting our paper IKFlow, Generating Diverse Inverse Kinematics Solutions. This work was done with my collaborators Bayard Ames and George Konadars. In this work, we present IKFlow, a novel approach to the inverse kinematics problem which is capable of generating diverse IK solutions in magnitudes of order time faster than current state-of-the-art methods. Inverse kinematics is the problem of finding joint angle configurations of a robot such that its end effector achieves some desired pose when it's in this configuration. This is a fundamental problem in robotics, as tasks are often best expressed in Cartesian space. However, we can only control a robot by setting its joint angles. Therefore, mapping from Cartesian space to the end effector to joint space is needed to accomplish tasks. As a concrete example, for the end effector of a welding robot to follow a specified path, the robot needs to find joint space configurations that move the end effector along this path. Importantly, while for 6 degree of freedom robots, there will be a finite number of inverse kinematics solutions, if any at all, for a given Cartesian target pose, for redundant robots, which have 7 or higher degrees of freedom, there may be an infinite number of solutions. Current solutions can be broadly classified into two groups, those that analytically solve the problem and those that perform a nonlinear optimization. Analytical solvers work by analyzing the robot's geometry in order to find analytic expressions that can be solved to yield IK solutions. The benefit of these methods are that you get an exact solution very quickly, for example, within microseconds. However, the downsides are that a redundancy parameter needs to be set, that portions of the solution set may be unavailable due to the use of predefined values that are used to handle the case of infinite solutions, and that certain solvers require an existing solution. In the other camp, nonlinear optimization methods work by optimizing a randomly initialized joint configuration. Optimization steps use the pseudo-inverse of the end effector's Jacobian in order to iteratively move the end effector closer to the target pose. The benefit of these methods are that they work out of the box for reasonable kinematic chains, and they generate arbitrarily accurate solutions quickly. The downsides, however, are that they will only return a single solution if one is found, and they may fail to find a solution even if it exists. As opposed to all other existing methods, IKFlow generates IK solutions in parallel on a GPU, which enables users to sample thousands of solutions in just milliseconds. Thus, IKFlow falls into a new category of IK solvers, in which an approximation of the entire solution set is returned when the solver is queried. The scene on the right shows a scenario in which IKFlow would be useful. The robot in this scenario is tasked with picking up a cup. However, portions of the solution space are in collision with the environment because of the kettle. When running IKFlow, a large number of possible solutions are returned, which can then be evaluated. Without IKFlow, an IK solver would need to be repeatedly called until either a valid solution was found or the program gave up. With IKFlow, however, the system designer can get all the solutions in one call before choosing one according to an application-specific criteria. Under the hood, IKFlow treats a set of IK solutions as a distribution and uses a conditional normalizing flow network to fit this distribution. The conditional normalizing flow can then be sampled from when solutions are desired. When sampling from the network, noise from a latent space is drawn from a Gaussian distribution and passed through each coupling layer in the network. The initial latent noise is transformed by each layer until the end in which it is interpreted as an IK solution. In this video of the Baxter robot, we demonstrate this mapping by showing how varying a latent vector changes the generated IK solution. The two plots on the left show the first 4 values of a latent vector, which is 15-dimensional for this particular model. At each time step, the IK solution generated by this latent vector is used to set the robot's joint configuration. We'll now look at our quantitative results. We trained models for 10 different kinematic chains on 6 different robots to validate our method. When testing a model, we measured the average positional and rotational error of the end effector when the robot's configuration is set to the IK solutions generated by IKFlow. The positional errors of the final trained models are all within 1 centimeter, which is a low enough error for many applications. The solutions can be easily refined using either traditional nonlinear optimization-based solvers or with the parallelized nonlinear optimization solver provided with the IKFlow software, which is available in the papers and company and GitHub repository. Next, we demonstrate our results qualitatively for the Baxter, Panda, and PR2 robots. The 3 robots use 25 IK solutions at every time step to get configurations which track a Mug's trajectory. In these motions, the same latent noise is used across all time steps of the trajectory. Because of this, there is smooth motion for each of the solutions. One way to think about this is that each of the 25 solutions is generating a potential motion plan. We see that the solutions are all highly accurate, with the exception of occasional erroneous ones. In the figure on the right, we see solve time as a function of the number of requested solutions for both IKFlow, TrackIK, which is the state-of-the-art nonlinear optimization-based solver that is used widely in the robotics world, and TrackIK solved seeded with IKFlow solutions. We can see that TrackIK generates a single solution faster than IKFlow, but at 6 or more solutions, it becomes faster to run IKFlow, or to run IKFlow and use the solutions as seeds for a TrackIK. Note that the blue line for IKFlow appears to stay nearly flat in both plots. This is because solve time is minimally impacted by the number of requested solutions, as the solutions are calculated in parallel on the GPU. Note that the runtime depends on the architecture of the underlying model. Smaller models will have reduced inference time. However, even our largest models are able to generate 100 solutions in under 10 milliseconds. For more details, please see our full-length paper. Thanks for attending this presentation. In conclusion, please check out our project page where you can find instructions on how to run IKFlow for yourself, plus see other demos, and also keep an eye out for IROS and movement packages. Thanks.